and then this equals this. So that will give you a fourth equation. Now if you wanted, you can get a fifth equation relating A, B, these constants, A, B, C, D, E, because these are just the matching terms, you know, matching the values and matching the gradients. But you could get a fifth equation if you wanted, and that's from normalization. Okay, so actually I don't think we need it, because all we're interested in is finding what's big T. You know, what big T here? What fraction of your wave, in a sense, comes through that heads off to the right, and what fraction, your big R, heads back, that gets bounced back, where R plus T has to equal 1. Right? So, well, if you did want to use the normalization, how would you do that? Well, you need to use the free wave. So I guess you would square this, integral 0 to L dx, something like that. And this is, I guess you integral 0 to A, all that squared, dx. And here I suppose it would be integral, I guess also 0 to L. It's not in the textbook, I'm just inventing this as I go. This squared dl, and you add all of those three, and you have to get 1, because you know, the particle is somewhere in those three regions. That's certain. Right? The particle doesn't disappear. Okay. Now, so, but what we're interested in is what's big T and what's big R, as defined in the previous session. So you're interested in these two terms here. So B is this waveform that heads back, that gets bounced back. So B squared gives you a measure of how strong it is. You know, well, what's the probability density heading back this way? And big T, corresponds to this one. And YE, well, because these here, that's your waveform that heads off to the right, that got through the barrier, right? So you don't need to solve for all 5 of these constants. Just B over A, just finding what BA over A is and what E over A is. You only need the proportions. You don't need to know the absolute value of A. Right? You just want to know what B over A is and then square it, or what E over A is and square it. And that will, these will give you your R and T. So I've asked you for homework, getting a bit tougher now. Solve all these. It's a bit tedious, but essentially it's just algebra. Well, a little bit of calculus and quite a bit of algebra, right? So I'll ask you to find what R is. The reflection fraction, of your wave that gets sent back, bounced back, and what fraction goes through, T for transmission, right? R for reflection, bouncing back. And given all these, and you do all the matching of gradients and values of the wave function at the 2 boundary points. So you get 4 equations for those, and that's all you need. You don't need to do the normalization thing. And so homework is prove that big T is of this expression, okay? And R, big R is this expression, okay? Well, now partly it's just common sense, but if the hill, this barrier here, of height V0 and width A, little a, if this hill is thick, in other words A is quite large, little a here is quite large, then Ka, big K, that's a term that involves V0. So if V0's high, and A is quite wide, then K. Just panicking there for a moment. It was the ping of my laptop, not my camera. I thought maybe I'd just run out, but should be okay. All right. So if Ka is much larger than 1, then shine goes very large, and therefore 1 over very large goes small, so big T goes to nothing. And that makes sense, right? Because what is big T? It's like the fraction that gets transmitted. But as your barrier gets taller and wider, then there's more space for this to fall down, and as large V0, the exponential rate of falling is high. So very little T, so T effectively goes to nothing. Now, the other extreme, if A is very, very thin, and your potential V0 is very short, not tall, then Ka is much smaller than 1, the opposite of here. Okay, and then and again, this is part of homework. If your Ka now is very short, so you can make approximations with this. Show that this big T becomes equivalent to this. Right? And so as VA is small, so V squared A squared is small, and so your T is almost 1. Okay, so the smaller your V and your A, the higher your transmission, your big T, the fraction that goes through. Okay, so you get good barrier. Here's your barrier. Good barrier penetration. The wave actually goes through. Okay, and this I just said a bit earlier that tunneling is technologically useful. Gets used in certain kinds of transistors, and it has theoretical value because you can explain so-called alpha decay, meaning it explains the radioactivity of heavy nuclei shooting out alpha particles, helium nuclei, because there is a barrier to those particles flying out. They have to penetrate that barrier to get out. And what is that barrier? I think it's just the strong nuclear force between nucleons, protons and neutrons. The strong force acts, and that's a potential. There's your potential. That's your V0. So for the alpha particles to get out, they have to tunnel through that potential barrier. So tunneling, technologically useful and theoretically useful to explain certain aspects of radioactivity. Okay, so till next session.